Hi everybody. Today we're going to go over how we calculate pharmacokinetic constants that are needed either at an individual level or a population-wide level to calculate concentrations, to calculate future concentrations, to calculate drug regimens. So these are really pivotal PK parameters that we need in order to use a lot of the equations that we use in drug dosing. So those pharmacokinetic constants that we're going to talk about are the elimination rate constant, or K sub E, the volume of distribution, sometimes you'll see this with a small d next to it, T1 half, or the half-life, and clearance. And so also today we're going to be talking about all of these PK constants apropos to a one-compartment model. So let's get started. The layout I have here is a table that shows different types of dosing. You have your bolus, intermittent infusion, continuous infusion, and extravascular dosing on the top row. And then below that, I have it divided by the frequency of doses. So we have single dose, multiple dose, and steady state dosing. And so each of those are captured for each of the dosing types. And then for each row, we have an equation that matches up to it, and we're going to see where this equation applies to these given doses and frequency of the doses. So let's start with the first one here, the elimination rate constant, or KE. Now generally you will see the units for KE in 1 over some sort of unit of time. Typically we write it out like hour to the negative 1. It could be minutes to the negative 1, but the most common we see is hour to the negative 1. Now, where does this specific equation here, which is a natural log of a concentration at a time, so C1 matches with T1, this is a given concentration of a drug at a given time, minus the natural log of another concentration over another given time. And another key point to this equation is it is negative on top. So where does this equation apply? And this first one's pretty easy. It applies to all the different dosing types and frequency scenarios. The only caveat here is with continuous infusions, two things. I put an asterisk next to the single dose because a continuous infusion really isn't a single dose, right? It's a continuous infusion. The only time that we consider it maybe a single dose is you're giving a continuous infusion to a patient and you haven't reached steady state yet. There, you can treat it almost like a bolus or a single dose to figure out PK constants, to figure out concentrations, and all those good things. For a steady state of a continuous infusion, we also incorporate what's called K naught over concentration times volume to calculate KE. So what is K naught? K naught is the infusion rate of the drug itself. So now that we have this first KE equation settled, let's go down to the next row and look at half-life, which is equal to 0.693 over KE. So these are related. Let's see where this applies. And if you couldn't have guessed, or maybe you did, because they're related, it applies to all of the equations again, or all the dosing and frequency scenarios that we have here on the slide. So those interrelated equations are ones that you definitely want to know because they're applicable to basically every scenario you will deal with. So another way we can relate these two equations is in the following manner. KE is also equal to clearance over volume, and T1 half itself can be transformed into 0.693 times volume over clearance, and that's because we plug in clearance over volume into the KE to get the flipped version here, 0.693 times volume over clearance. This can be useful in case you don't have concentrations, but in a problem or a scenario you're given volume and clearance. So it's good to know how they relate and how you can kind of change out some of the parameters given what you have in a certain problem or case scenario. And another thing I forgot to mention here, T1 half is in units of time, so it's usually in hours. So again, because KE and T1/2 are related, it's just hours versus KE is 1 over hour. Now, let's move on to the next one, which would be volume of distribution equals the dose, which would be in milligrams, over concentration. So if you actually kind of crossed out those, you get units here of something related to volume, liters, milliliters. It just depends on the drug. So where does this equation apply? It applies in two scenarios, the single dose for a bolus. So again, I know it's a little weird to think of a bolus dose as multiple doses or reaching steady state, but that is possible. So it's very similar in terms of the single dose of a bolus or a single dose of an extravascular dose, which we tend to think of oral dosing. So oral dosing can be thought of kind of a bolus type of dose. So what does V over F mean here? It means that you have to incorporate the bioavailability factor. So that's how the equation would change here. So either you'd have to put the F up here, or you just have to write V over F equals whatever you are able to solve for. Let's go down to the next volume of distribution, which again would have a unit of liters. And this one is calculated by dividing the dose by a concentration minus a previous concentration. So pre-dose can mean previous concentration. It can mean 0 if the patient hasn't had the drug yet. So pre-dose just means anything prior to your initial concentration that you're, or the C0 that you're measuring here. So where does this apply? And it's kind of on the other side of what we just did. It applies to the multiple dose and steady state dosing for both bolus and extravascular. Again, if you're doing extravascular, you have to incorporate the bioavailability factor, because with extravascular dosing, there will be some sort of bioavailability in play. When you're doing IV dosing, obviously the bioavailability number is 1, so we just remove that from the equation. Finally, let's take a look at this last messy looking equation, which incorporates the infusion rate, and it's 1 minus an exponent to the elimination rate times T prime, which is actually the infusion time. So that's what T prime is here. That's a good thing to remember and know. And that's divided by, again, the elimination rate times a max concentration minus a C pre-dose, so a previous concentration, to an exponent of the elimination rate, and again, that infusion time. So where does this apply? So it applies in their intermittent infusion, because those have infusion times. So if you have an infusion times of 30 minutes, that would be your T prime. If it was 60 minutes, that would be your T prime. And remember, we have to make the units match. So whatever your other units that you're calculating for, or what you're shooting for, that's what you want to use for either 30 minutes or maybe 0.5 hours. It just depends on the context and the scenario. And finally, it is used for a quote-unquote single dose scenario for continuous infusion. And that's again because steady state hasn't been achieved, so you can treat that time on a continuous infusion as the T prime there. Okay, so let's finish up pharmacokinetic constants. We've done elimination rate, we've done volume of distribution, we've done T1/2, that just leaves clearance. So again, we have the same setup here. We're looking at one compartment models. Let's take a look at where this clearance, which is equal to the elimination rate times volume of distribution, applies. And so clearances are usually some sort of units of volume over time. And the most common one we see is liters over hour. So that's the general one you see. Sometimes you'll see milliliters over minutes. Really just, again, depends on the context in the situation. So where does this first equation apply? So this first equation applies at everything except for continuous infusion. And for the extravascular dosing, kind of similar to what we've talked about before, you have to incorporate bioavailability, which here would end up underneath the V. So if you know the bioavailability, that's where you plug it in. If not, some people just leave it within the answer of the equation, the F. It just depends. Now, let's go down to the next equation. Clearance equals K0, so infusion rate times the concentration at steady state, and one could guess where this would apply. Because it's a steady state, it has to be a steady state scenario. Because it's an infusion rate, it's going to be a continuous infusion. So that's how we calculate clearance for continuous infusion. Finally, this last one is a special type of situation. And this equation's for any route at steady state. And it looks like dose over tau. So tau is the dosing time or dosing interval over the concentration at steady state. So where does this apply? And like I said, any route at steady state is where it applies. So bolus at steady state, intermittent infusion at steady state, continuous infusion at steady state, and extravascular dosing at steady state. So it's a pretty neat equation, and that it's very versatile. If you are able to have these parameters in your problem or your scenario, then you'll be able to calculate clearance pretty quickly. So that's how we calculate pK constants for various given dosing scenarios. Thank you for your attention.